Hi. Okay, in the section that we're looking at now, what we're going to do is talk about the major data types in Erlang and how those are different from things we're familiar with, but how they're also similar to things we're already aware of. So we have 6 different kinds of data in Erlang, 6 different kinds of values that we can compute with. We have numbers, we have atoms, booleans, we have tuples and lists, different ways of putting composite data together. We have strings and we have functions. And just to highlight what's different perhaps from other languages, I'll say rather more about atoms, something about tuples and lists, how they're similar, how they're different, and finally about functions. But as we go along, I'll talk about the other sorts of data as well. So let's get started by looking at numbers. So numbers in Erlang can be integers and floats. Erlang is weakly typed. We're not forced to say what types a function will take. It can take something of any type. The numbers, the integers, are big nums, so they are arbitrarily large numbers, full precision numbers, just by default. So for instance there you can see a very large number of powers of 10 multiplied together, and the answer we get is exactly right. In a similar way, what I'm doing here is calculating something like a product of the list of numbers that you see in there, jumping ahead a bit, using a function called foldr, which is like reduce in a map reduce. And what that's doing is multiplying all those numbers together. And again, you can see that product. We've got a large product, which is completely accurate. We don't have any integer overflow there. So we have integer big nums, but we also have floats. We can use different bases, so we write numbers to a different base by putting the base followed by a hash followed immediately by the number in that base. So if we write 2 hash 100, we get the number 4. If we write 3 hash 34, we get illegal integer because, of course, digit 3, digit 4 is not a legal number base 3. It would need to consist of the digits 0, 1 and 2. So we can use those different bases. In particular, we can use hex and octal and so on. We have all the usual operators, plus, minus, times, and slash for floating point division, div and rem for division of integers. So if we write 12 div 5, we get the answer 2. If we write 12.0 div 5, we get an exception error, because what we've done is invoke an integer operation on floats. And that's typical of Erlang. We are getting a runtime error from that rather than it being signalled in advance. So we could perfectly happily write something like that in a file inside an Erlang definition. It would only cause an error at runtime. Okay, so that gives us, the numbers are pretty much like numbers in other languages, except we have big nums and we can use different bases. Atoms are perhaps unfamiliar. Atoms are data which simply stand for themselves. So if I evaluate the atom foo, which I just get by writing a string beginning with a small letter, the answer to that is foo. It doesn't stand for anything else, it isn't a variable, it's simply a data that says foo. And in general, I can enclose any string of characters between single quotes, and that will be an atom. So atoms simply stand for themselves. Now the computation we can do with atoms is we can compare them for equality. So you can see there that foo is equal to itself, but it's not equal to I am an atom. We can also order them. So foo is greater than the atom I am an atom. I guess according to a lexicographic ordering, based on the ASCII codes of the characters, one assumes. And because we can compare them for equality, we're going to be able to use them in pattern matching, which is something that we'll be coming across a bit later on. But that makes them very useful in general data representation. So we use them on their own. So for example, there are 2 special atoms, true and false, and they represent the booleans. There isn't a separate type of booleans. Those two atoms together are the booleans. And we'll see that we can match against those, but also we can match against atoms as components of bigger data structures. So that's nice. We can put values together. So a tuple is a number of pieces of data enclosed in curly braces. So here we've got 3 pieces of data: the string Joe, the string Armstrong, and the number 55 form a tuple. Here we see 2 pieces of data, 2 floating point numbers put together in a tuple. Here we see 2 tuples put together to form a tuple. You can think of this as representing the bottom left and top right corners of a rectangle on a Cartesian plane, for example. What we commonly do, Erlang is an idiomatic language, and one of the ways that we represent data is by using tuples, and we use the first field in the tuple to describe what sort of data we've got. So in the first case here, we're saying we have a rectangle and it has 2 further components, which are indeed the coordinates of the bottom left and top right corners of the rectangle. The second tuple that you see here is representing a circle. It's got the second component is a pair, representing a coordinate pair, and the third component is a single number representing the radius. So you can see that we're describing complex types, building them up explicitly using tuples. In other languages like Haskell, we might describe a new data type for shapes like this. What we do in Erlang is represent them concretely using tuples and atoms and other data representations. So that's what we see for tuples. And typically, the examples you can see here are heterogeneous. We've got different types in different fields. In the circle example, the first field is an atom, the second field is a pair, the third field is a float. And you can think of a tuple as like the set of attributes of a Java object. Okay, so that's one way of putting values together. Lists are collections of values. So a list has a number of pieces of data. For example, here we've got a list with 2 elements, the string Joe and the string Armstrong. Here we've got a list with 1 element, which is itself a tuple. Here we've got a list with 2 elements, which are both tuples. Here we've got a list with no elements, it's an empty list. And here we've got a list with 1 element, which is itself a list of lists we have there. Now typically lists are homogeneous, all their elements have the same type. And you can think of lists as being like the collection types in Java. It's a way of putting together data, and the things we might have lists of numbers, we might think of lists of numbers as a single type, and of course different things in that type have different numbers of elements. So we have both tuples here and lists. So why do we have both? We can have the list with 3 elements, Joe, Armstrong and 21. We can have the tuple with Joe, Armstrong and 21. So why do we have both? The answer is quite subtle. The answer is that we can do different things with lists and with tuples. We can think of lists as being built up 1 element at a time, so we can iterate through the elements of a list, for example. That's not something we can do with a tuple. We just see the tuple as being built in one go, so we can take all the elements of the tuple. But we'll find out more about this next week in the MOOC. Now, one type I mentioned was that there are strings in Erlang, and strings in Erlang are simply lists of characters. So the string ABC, if we print that, we get ABC. But if you look at the list 97, 98, 99, that actually prints out as the list ABC, and that's because 97 is the code for the character A, and we can actually write that out explicitly and say the list consisting of code for character A, code for character B, code for character C, and we get the string ABC. But if you look at the second example there, you can see that sometimes the Erlang print in the Erlang interpreter can give you some rather peculiar results. You print out a list of numbers and it gives you a rather peculiar string. That's what's going on. It's interpreting that list of numbers as a string of characters. And as I said earlier, if we want the ASCII code for a character like C, we prefix it with the $ symbol. Now finally, and perhaps most novelly, we are able to have functions as data. So for example, I can type the function that takes the value x and returns the value x times 2. You can see the syntax of it there. It begins with fun, ends with end. That is evaluated in the Erlang shell to give us a function. It can't be printed out properly because you can't print out what a function is, but there it is. And functions can then be arguments to other functions. So we have built in to our lists module, we have the map function, which of course I'm sure you're aware of. What map does is it takes a function and a list of things and applies that function to every element of the list. So in the example you can see here, the first argument is a function that takes x to x times 2, so it doubles a numeric element. And if we've got the list of numbers 1, 2, 3, 4, we get as a result the numbers 2, 4, 6, 8. In a similar way, what foldr does, foldr is reduce in other terminology. What foldr is doing here is combining all the elements of the list that we see using the operator star. And what this is doing is, in this case, is calculating the factorial of 6. It's 1 times 2 times 3 times 4 times 5 times 6. And that gives us very sort of powerful data manipulation, map reduce style that we see in Hadoop, and the sort of data manipulation that's in the D3 library, which is a library for JavaScript. So these sorts of functions are used not simply in functional programming, but are used in functional programming idioms in a number of different programming languages. We'll come back to this later on in the second and third week of the MOOC. So just to recap, we've seen that the values in Erlang are numbers, they're integers and floats, atoms, which simply stand for themselves, the booleans true and false, which are 2 examples of atoms, tuples and lists, which are collections, but which can be processed in different ways. Tuples are more like records in other languages. Lists are more like collections. Strings are lists of characters. And finally, functions are values themselves. They can be arguments of functions and return values of functions too. And so functions are, in the words of Christopher Strachey, first-class citizens. Okay, what we'll do now is do a quiz to see how much of what you've absorbed from what we've just been talking about. Thanks very much.